Greetings. Welcome back, and we're heading into Unit 3 of AP Physics C Mechanics, which is the Work and Energy unit. This first chapter is going to be mostly review. If you've taken a physics class before, I'm going to be covering the definitions of work, power, and how all of that ties into energy. I'm also going to be introducing a new math tool towards the end because work is defined a little bit differently in Physics C going forward, and it's a tool that you should know for a lot of the other equations we'll find in the future. So without further ado, we've got simple machines first. And the reason I like to start with these is A, because I love them personally. They are super cool. But also, really these machines were partly the reason why we developed work and energy as a concept in the first place. And really these machines were invented because historically one of humanity's biggest enemies is gravity. Particularly because gravity makes the process of lifting heavy objects significantly harder. And this was a problem that lasted for millennia. But humans are pretty smart, and they developed these really simple machines, some of them extremely simple, that allowed us to lift these objects and build things like the pyramids. So part of what led to the development of these machines was that we as humans kind of understood that we could perform the same task with less perceived effort, which I guess would later be defined as force, if we decided to perform that task over a greater distance. So we kind of spread the task out over a longer place or over a longer distance to make the task feel less terrible in the moment. It's kind of like riding a bike over a much smoother hill over a significant distance. Sometimes when I'm riding a bike, I don't even realize how much elevation I had gained because the grade of the hill was so small. So one of the simple machines that was invented, one of my favorites, was the pulley, particularly the block and tackle. And while a pulley, at its simplest, allows you to just kind of redirect the force that you need to apply in the direction of to lift an object, you could also use this to maybe involve more people in the process of lifting an object if, say, you got 10 people to go and pull on this rope here to lift the object. But also, with this particular setup right here, called a block and tackle, the fact that the tension stays the same throughout this whole rope allows us to kind of loop around the rope around these pulleys in such a way that the force that we apply gets doubled when lifting the object up over here. It's very fancy, but it does also lead to you needing to use more rope in order to lift the object, and that's where that exchange comes from. Another simple machine, arguably more simple than pulleys, was the lever. You take this fulcrum here, or this pivot point, you place some kind of flat object along it, and you find that really the farther along that object you pull on or push on, the easier it is to perform a task for something that is a lot closer to that pivot point. So here, if you were trying to lift a refrigerator with a lever, you would want to push on the opposite longer end in order to lift the object on the shorter end much more easily. And again, the trade-off there is that the distance that you have to push the plank through is significantly higher than the distance that the fridge gets lifted through on the other end. And finally, the inclined plane, which hopefully we're pretty familiar with from physics problems in the previous unit. But an inclined plane, the principle behind that is very simple. In this case, the surface of the incline, its normal force, in fact, is sharing some of the load of the object's weight. And so you're not having to constantly be carrying it up this incline. And so you push this object up the incline, and you are still pushing it through the same vertical distance as you see here, but you're able to push it through the greater distance of the hypotenuse of this incline, thus spreading out the work over a longer distance. So all of these objects were used by humans for millennia, and the equal trade-off between force and distance that was kind of utilized with these devices is what eventually led to the idea of work. So in exchange for all of that is a quantity that was starting to be thought of, which is energy. And energy has kind of a weird definition in physics, but I like to define it as a quantity available to something that allows it to do work or to apply a force. So think of it as almost like how much money is available to something, in cash in their wallet. Energy can be spent, like money can be spent, on things like velocity or height, etc. Energy can be earned, or money can be earned, and that's usually through work being done either on the object or the object is doing work. And then finally, energy can, of course, be exchanged from one form to another. That comes from the principle that energy cannot be created or destroyed. And there are lots of different types of energy that you could kind of exchange or spend or earn. We've got kinetic energy, rotational kinetic energy, where things are spinning around. Gravitational potential energy, which may be familiar from a lot of different classes in the past. Elastic potential energy from stretching rubber bands or springs. Light and electromagnetic energy, which is quite literally everywhere around you all the time. Chemical energy, which generally is released in chemical reactions in the form of thermal energy, which is related to heat and temperature. Electric potential energy would be almost the a tie-in to electrostatic attraction or repulsion that you sometimes see with static electricity. Nuclear and atomic energy, which of course provides a significant amount of energy, normally in nuclear power plants. And finally, mass energy, which is very similar to nuclear and atomic energy, but we can think of mass in modern physics as being a form of energy in of itself. But that is a topic that we'll have to put off to another day. And so the other side of energy is officially the principle of work, which again was kind of understood by people, by humanity for a long time, but was officially formulated in physics actually fairly recently, sometime around the 1800s officially. And so in physics, work, denoted by capital W, is defined as the amount of energy transferred to or from a system by a force or a push along a certain displacement, which is denoted by D. So for instance, like if you're just lifting an object, you do work by applying a force to some sort of heavy object, lifting it through a vertical displacement D. And then if you were to drop that object, then suddenly you're not touching the object anymore, but the force due to gravity certainly is. And so it would be gravity doing work on the object, pulling it back down through that same vertical displacement down to the earth. And we would consider both of those works to be the same, because you have to apply the object's force due to gravity to lift it, and then force due to gravity obviously has to apply itself back down. So in a way, work ends up being the same under things like gravity going through different displacements. Work is a scalar quantity, meaning we won't really have to worry about direction as much. However, it can be positive or negative, and sometimes the idea behind that can be a little confusing. So in general, if you have a positive value of work, that just means that you're adding energy to a system. So somebody is pushing this trolley, and that trolley is gaining some kind of energy, usually kinetic energy, if we're in mechanics. And then conversely, if something is negative work, generally that means that we're considering for that specific subject of the problem, that energy is being removed from it. So it's slowing down, or it's losing height, or it's just straight up losing mechanical energy due to friction or something. That would all be negative work. And the SI unit for work and energy for that matter is the joule, capital J. It was officially defined by James Prescott Joule in the 19th century as the work required to exert 1 Newton of force through a displacement of 1 meter. So if you took some 1 Newton object, lifted it 1 meter, you have done 1 joule of work. And so for that matter, you can technically define a joule in terms of simpler components, where you could say 1 joule is effectively 1 Newton meter. Note that we actually tend to try and avoid using Newton meters to as units of energy, because there's going to be another unit, torque, that we cover in the rotation unit a little later on that uses these exact same units. And so things get a little confusing, so we try to avoid Newton meters for energy. And so on the similar topic with work, work we consider to be the product of the force acting on the object that's parallel to that object's displacement. So if we wanted to formulate work and calculate it, generally we have 2 equations that you see most often. In an introductory physics class or a first-year physics class, if it's not calculus-based, you generally see it as work equals force times distance, or maybe force parallel to times distance. And these little vertical lines here are just indicating that we need to make sure that the force being multiplied by the distance is parallel to that distance. The more detailed version, or the one that we're going to be using in this class, is work is equal to F dot D, or in other words, that equals F times D times the cosine of the angle between them. So two vectors, no matter what, whatever angle is between those two vectors, that's the angle that you plug in to this formula right here. So just as a basic example, say you just have like a fellow that's pushing a box over a 5-meter distance, and they're applying 12 newtons of force constantly through that distance. Well, the force, the work that they would apply would be 12 newtons times that distance of 5 meters, or about 60 joules worth of energy. So we would say as a statement that this person did 60 joules worth of work on this box. For now, there's one more term that we want to cover, which is power. And I guess to start thinking about power, I'm going to use a specific example here of someone doing pull-ups on a bar, something that I am not very good at personally. And so when you are doing pull-ups, again, primarily you're doing work against humanity's arch nemesis, gravity. So I'm just going to say generally, if we're using this image here, a displacement of delta y maybe is what this person is moving through, and they're doing work against gravity. So the work done for one pull-up would be force times the displacement, or force of gravity times delta y. So you're doing work, the force you're applying is your own force due to gravity, and the displacement is delta y. So in general, say two people were completing 6 pull-ups, and the energy that they both spent was about 6 times the work of one pull-up. So they both spend the exact same amount of energy. Well, say person A does 6 pull-ups in 40 seconds. That would probably be me. And then person B does 6 pull-ups in 4 seconds. Well, I'll let you think about that for a second. Which one do you feel like is more powerful? Well, if you said person B, I would kind of tend to agree with you with that. Doing 6 pull-ups in the span of 4 seconds feels pretty impressive. And that's really how you want to think about power as well. Person B here spent the same amount of energy as the other person in a significantly shorter amount of time, about 10 times less. So you would say that their feat is more impressive, or they're more powerful overall. So power in physics is defined as the rate of change, or the derivative, if you're using calculus, of work or energy with respect to time. So it's how much work you're doing within a certain interval of time. Power has 2 main types. In algebra-based physics class, generally you see it as average power, which is delta E over delta T, or change in energy over change in time. Or it could also be defined as the amount of work someone's doing over a change in time, delta T. In physics C, because we have calculus under our tool belts, we could also define instantaneous power, which would be the derivative of energy or work with respect to time. The units for power are, well, I guess joules divided by seconds, if we're taking the equation here literally. But officially, it is defined as the watt, which is denoted by capital W, and that is officially joules per second. Now, there's one more equation for power that is pretty helpful, and in fact, it appears on the AP Physics C formula sheet. And so we're going to derive it first with a bit of substitution, where our goal here is to express power in terms of force and velocity. So if we start with a basic, but maybe a little reframed formula for work, which is force times some displacement x, I'm going to suppose that we shrink it down a little bit so we have an infinitesimal amount of work. So a very small amount of work that would equate to force times some very small displacement. So force is the thing that we're holding constant here. If we take that and we plug that into our formula for power over here, so dW over dt, well, substituting our formula over here into that, we've got F times dx over dt. And what we're going to do is just rearrange things a little bit. So F is kind of pulled out of that, and we're left with F times dx over dt. And if you pay special attention to this little guy right here, you might notice that that technically can be condensed down into a single variable, where we can express power in terms of force times velocity, or the rate of change of position with respect to time. So officially, power in terms of force and velocity is the dot, or careful, spoiler, would be force dot velocity equals F times V over times cosine of theta. So you can take the force, multiply it by the velocity and the cosine of the angle between those two things, and you will get the power exerted by the thing applying that force. Cool. So you notice I tripped up a little bit there. It's because I got a little ahead of myself mentioning a math tool. And that's that you might have been wondering why I'm referring to this as a dot and not just F times D. And so the last thing I want to do is show exactly how this right here, this F dot D, turns into this, F times D times cosine of theta. And that comes from a new math tool that I want you to be aware of, which is known as a dot product, also known as a scalar product in some cases. It's denoted by this over here. So you have a vector A and a vector B. It would be A dot B. And a dot product is simply a way of multiplying two vectors together that results in a scalar quantity. Now that's a little abstract. And so in physics, generally these things are used to model scenarios in which two vectors combine into a maximum value when parallel. Notice if we watch this thing here, when they become parallel, that's when this number is going to be at its maximum at either 1 or -1. We'll watch and follow one more time. And then it starts falling. Cool. And they will equal 0 when the vectors are perpendicular. Notice the same thing happens here. This pops up in a lot of scenarios. The first of which, I suppose, is work. Remember, we want the force being applied to the object to be parallel to the displacement in order to consider doing work. And so the maximum work done by a force occurs when it's fully parallel to the resulting displacement. So we are defining in physics work as a dot product. And that's where that cosine of theta comes in on the equation as well, because cosine maximizes when two things are parallel and minimizes when the angle between things is perpendicular. And so formula-wise, how you can calculate a dot product really boils down to two different methods. If you have two vectors, A and B, like this, that are split into their components already, then the dot product is going to have you take all of the x, y, and z components of both vectors and multiply all of them together and add them up. So ax will be multiplied with bx, and then we'll add that to ay times by, and then we'll add that to az plus bz. And note here, we're kind of throwing out the direction when we do that. So a dot b in the end will be a scalar quantity. It kind of loses all sense of direction when we do this. We'll get one singular number out of this. The more common form of a dot product is the one that you see in the work formula, which is that if we have two vectors A and B, both with magnitudes A and B respectively, and an angle theta between them, then a dot product officially is defined as A times B, or the magnitudes of A and B, with multiplied by the cosine theta, or the angle between them. And this is a tool that's going to pop up in a lot of different equations that we'll find throughout this class, even going into E&M. So it's something to be aware of and to look out for, because it can give you information conceptually about when something might be at a maximum or a minimum. You just never know. So keep this tool in your tool belt in the back of your mind. And with that, I'm just going to run through some basic examples of work in a couple of different physics problems. And that will be the end of this video. So without further ado, let's do some examples. Right. So our first example here is fairly simple. We've got a block being dragged along a rough horizontal surface by a force F equals 200 newtons at an angle of 30 degrees with the horizontal depicted over here. We also nicely are given the friction force outright, which is 120 newtons, and that resists the object's motion through a displacement of 20 meters. So all of these forces are being applied through a distance of 20 meters. So we're being asked to find the net work done on the object, or the total amount of energy that's either gained or lost by this object due to each of these forces over here. So there are a couple of ways you could do this. Option one is right here, to take the net force acting on the object. So we add all the forces in advance, and then we multiply those by the displacement d, and then if there is an angle present between the net force and the displacement, we'll need to add in that cosine factor as well. Another option that you could potentially do is to find the works due to the applied force and the force due to friction separately first, and then you simply add those works together, because now remember, they have become scalar values. Note though that one of these works, namely friction, will probably be a negative value, meaning it's taking away energy from the system of this block. And so it's going to be this battle or this balance between the person applying the force and friction trying to take away energy from that system. I'm going to go ahead and do both ways here, just so we can learn a little bit more about the individual works over here. And so I'm going to start with the fast way, so we can just go ahead and solve the problem outright. And then when we do this one, we'll be able to check our work a little bit. So if we do it the first way here, we're going to first start by finding the net work or the net force on the system. So the net force here, in my opinion, is going to be comprised of the x component of the applied force over there, minus the force due to friction over there. So if we expand this out a little bit, we've got our force F, which will be 200 newtons, times the cosine of that 30-degree angle, minus the force due to friction that is simply given to us here. We don't need to calculate it, thankfully. All right, and if we do that, and we multiply that out, we'll get a net force of about 53 newtons, give or take. So now that we have that, we're going to go over here and we're going to calculate it using our formula. So the net work will equal the net force of 53 newtons, the displacement of 20 meters. And note that we found the net force in the x direction over here. So it's kind of pointing along this direction. And now the question here doesn't specifically state which direction it's displacing in, but we can kind of infer through the direction that we suspect its acceleration would be in, that this object is displacing to the right in the x direction. Because of that, the displacement is parallel to the direction of the net force, which is to the right. So the angle between the two here is 0 degrees. So we could just plug in a 0 for that cosine. That's going to mean that our cosine goes away entirely, or it becomes 1 rather. And so we're left with 53 times 20, which will be about 1,060 joules worth of energy that's added to this block altogether. And that is including what friction is taking away. So we have found a one and done solution to the problem right then and there. Pretty nice. Now let's try it out the other way. If we find those individual works, and we'll be able to check our work as well. Haha. So the first one is the work due to the applied force. So here it's going to be just the force itself times the displacement times the cosine of the angle between that force and the displacement, which again is in the positive x direction. So our force being applied is 200 newtons. The distance that we're moving through is still 20 meters, nothing changed. And the angle between the two here is 30 degrees. So we're going 30 right there. And again, it's because we are looking for the angle between those two vectors specifically here. So if we calculate that, it'll turn out to be about 3,464 joules. All right. Now notice that is larger than the net work that the object gained at the end of the day. And that's because, again, there is a delinquent afoot here that we're hopefully going to find with this next force that's sapping away energy that we, as the individual pulling this block, are putting in. So next, let's take a look at the works due to the force of friction. And it's getting a little weird with the subscripts there, I apologize. So here, we're going to multiply the force of friction directly with the displacement and the angle between those two vectors there. Now note here, the force due to friction technically does have an angle that isn't 0, although it is parallel technically to the positive x direction. If you note, it's about a 180 turn from the positive x direction, what we would consider, to the force due to friction over there. So we're going to be plugging in an angle of 180 degrees to our formula over here. So we have a force due to friction of 120 newtons, multiplying that again by a displacement of 20 meters. And again, cosine of 180 degrees is our angle. And if we calculate that, we'll end up getting negative 2,400 joules. So that's a lot of energy being wasted due to friction. And so our last step here is to simply take these works and add them together because they are now scalar quantities, although the negative sign definitely still matters. And so the net work will be the sum of these two. So 3,464 minus 2,400 is going to be about 1,064 joules, which note is a little off from what we calculated over here. That's mostly due to me playing fast and loose with rounding. So do not worry about that. These numbers should equate to the same thing if you stick to a consistent system of rounding. So 2 different ways to solve for work. Just know that, again, you can always solve for the work done by an individual force if you're not necessarily looking for the network. That's an important distinction to make that you should pick out in the wording of a problem. All right, so the last part here is asking if the situation occurred in a time interval of 10 seconds, what is the average power output of the person applying force F? So this is what I mean, be careful. It is not asking about the power output of the net force on the system. It is specifically asking about the power output of the person applying the force. And so we should be thankful then that we found those individual works over here, because we are finding the power output of this work right here, the 3,464 joules. That is what the person personally is putting into this system. So over here, power is defined as the amount of work put in over an interval of time. So here, thankfully, we already have that down. That's 3,464. Maybe I'll denote this as the work due to the person. 64 joules over a time interval of 10 seconds. And so the power output of this person is 346.4 watts, or joules per second. Note that this value, this power output here, is about half a horsepower over here. So this person's putting in work. They're really trying to pull this box. Good job, person. All right. So this problem is just kind of nice for reminding yourself about picking out works for specific things as opposed to always just a network. And so on this next problem, we're going to take a look at gravity specifically. This one looks rather intimidating on first glance. We have a block that's starting from rest at a height equal to the radius of a circular track right here. The block that's starting at rest here has a mass of 2 kilograms and it's sliding down this quarter circle under the influence of gravity and gravity alone. So our goal here is to determine the work done by gravity on the block by the time it reaches the bottom. Now, the lesson I want you to learn from this one is something that we're going to get to later when we get to the concept of conservative forces, which is that gravity doesn't really care about the path that an object takes when it reaches the bottom, at least in terms of energy. And the reason for this is because of our formula for work. So if we write that out, we said conceptually that work is equivalent to the force times the displacement that would be parallel to that force. And work means it, especially with gravity. So here, note if we zoom in to make our little free body diagram, well, we've got a force due to gravity that's always, always, always pulling straight down on this block. That would be mg right here. And I guess technically at some points in this problem, especially as the block starts moving with respect to the track in circular motion, you could say it also has a normal force that's pointing centripetally towards the center of this circle, at least quarter circle that's been created here. Now note what the actual displacement of this block is from the top of the path to the bottom. The block starts at a point right here and travels all the way down vertically to here through a distance of 5 meters. Now that specifically is the displacement that would be parallel to gravity, because gravity is consistently pointing in that vertical direction. So if you're trying to find the work done by gravity specifically, all you need to do is find the vertical displacement downwards. So a little concept blurb here that maybe you could note down on this as you're working through this problem is that generally, anytime you're finding the work due to gravity, you can simplify the problem a lot by just figuring out how much the object displaces vertically, because that's the only displacement that you'll need to multiply by the force due to gravity to get this thing. So with that, I'm going to simplify this problem a little bit by saying the work due to gravity here is the force due to gravity times the displacement, in this case, in the y direction. So the force due to gravity here would be mg times this vertical displacement here, dy. So now let's go ahead and plug in our numbers. Our mass is 2 kilograms. Our acceleration due to gravity, for once, I'm actually going to use 9.8 meters per second squared here. And our vertical displacement, we said, was 5 meters because that is the radius of the circle. And so altogether, that is going to equal, go figure, about 98 joules from beginning to end. So that is how much energy this block has gained by the end of the problem, due to gravity at least. Now, another thing to note, a big conceptual piece of this problem is what the normal force is doing through all this time. And this is a concept that I want you to write down and always consider, which is that here, the normal force is acting as the centripetal force. It's the thing that's pushing the object constantly towards the center of this circular path that it's moving through. And in general, centripetal forces by definition are always perpendicular to the path that the object is taking, at least in perfect circular motion. So if an object is in circular motion, namely uniform circular motion, so the object isn't accelerating tangentially at all, then any centripetal forces do zero work on a system. And again, the reason for that is because in circular motion, note that the object is never moving towards or away from the radius of that circular path it's moving through. And so any forces that are pointing towards or away from the radius of that circle at any point, by definition, are perpendicular to the displacement that the object is moving through. It is not moving in the centripetal or centrifugal direction. So anytime you have a circular motion problem like that, just know anything that's centripetal or centrifugal does zero work. For instance, the normal force in this particular problem, it does zero work. All right. So that is all I wanted to extract from this problem. It's a lot more concept heavy than it is math heavy. But I wanted to use these two examples as a way to just get us thinking about works again. And in the next video, we're going to start implementing a few more nice math tools before we play with some deeper ideas in the realm of conservative and non-conservative forces. So until then, thank you for watching this rather long video, and I will catch you in the next one. Farewell.